Good afternoon, everyone, and welcome to the final 2025 Archaeology Month Learn at Lunchtime workshop hosted by the State Museum of Pennsylvania. I am Andrea MacDonald, Director of the State Historic Preservation Office. It is my pleasure to introduce today's topic and speaker. We will learn how buried soil horizons form and their importance to archaeology. Sharing his knowledge on the subject is Brian Fritz, owner and principal archaeological investigator for Quemahoning LLC, a cultural resources consulting firm. Brian holds a Bachelor of Science in Geology and a BA in Anthropology from Clarion University of Pennsylvania, and a Master of Science in Geology from the University of Akron. He is a registered professional archaeologist with 20 years of experience in conducting archaeological excavations, and he previously served on Pennsylvania's State Historic Preservation Board. In today's presentation, Brian will discuss how the land preserves clues to ancient human activity and how soil can be one of archaeology's best storytellers. He will share how one of the most important of these ancient surface layers, a buried soil horizon, can show where people once lived, hunted, or traveled. Welcome, Brian, and thank you for presenting today's program.
Well, hello, and thank you for inviting me here today. I'm delighted to be here. And I'm going to launch right into this.
Yep. Well, Brian sets up his presentation. Let me remind the audience to submit any questions about today's topic in the Q&A feature, and Brian will answer them after the presentation is complete. So, Brian, when you are ready, let's begin.
All righty. Well, as archaeologists, we spend a lot of our time digging in the soil and looking for clues to past cultures, but we don't often talk much about the soil itself. So I'm going to step through some of the processes today of how the soil forms and gets there, and what that can help us, and how that can help us learn about the archaeology and the cultures we're trying to understand. So let's see here. Whoop. So the first thing I want to stress, we want to talk about soils and soil horizons. So soil is that the stuff that you can dig into with hand tools and shovels. And we divide the soil up into identifiable horizons. Now, everybody's probably familiar with the topsoil. That's what we plant our gardens in and what the farmers farm their crops in. That's that rich organic soil that's at the ground surface. We call that the A horizon. But if you remove the topsoil, you expose that lighter killer soil underneath that it's a little lighter. It's got a little more clay rich. We call it the subsoil. We identify that as the B horizon. And if you dig deep enough, especially in river sediments, you'll eventually get down to a layer that's sand and silt that's relatively unweathered. It's kind of never been exposed to the surface very long. And we refer to that as C horizon. It's really not soil, it's just sediment. So what is really important to understand is that soil horizons form in sediment over time. So an A horizon and B horizons are not deposited. They form in sediment. So you start out with a new sediment over top of maybe a layer of gravel, and eventually organic matter accumulates on the surface and forms that A horizon, that organic rich horizon, and eventually a B horizon will form underneath that A horizon. So let's look at some examples of some soil profiles from the archaeological digs that I've conducted. This is a profile on a river terrace along Red Bank Creek in Clarion County. And if you look at this, you can see that there's multiple buried A horizons, those rich, organic, rich topsoils. And there's, I don't know, there's probably 1, 2, 3, 4, at least 5 there, maybe more. In another example, here are 5 or 6 buried A horizons. And these are very complex soils. They multiple layers, there's all kinds of things going on. And there were archaeological deposits in some of these buried A horizons. So how do we get that kind of buried soil structure? here's an example of what might be a typical ideal example of what a buried soil horizons would look like in Western Pennsylvania. And we have that surface horizon, that's where your current topsoil is. And then down deep, we have an A, B. Little b stands for buried. And then the second one down even deeper. So let's step through this process. So our streams and rivers, the actual stream channel tends to migrate back and forth across the river bottom, the valley bottom. Now, we don't really perceive this because this happens over time periods longer than our human lifetime, unless you really pay close attention. But eventually the stream channel will move. And when it moves, in this case, moving to the left, it leaves behind first a gravel bar. And those cobbles and pebbles represent the former stream bed. And that's our first layer. That's our first deposit, that gravel bar. Then eventually we get a flood, and some new sediment, some sand will be deposited over top of that gravel bar, and that's the beginning of our soil profile. So that'll be our sea horizon. It's new sediment, it's fresh, it's never been weathered yet. Then we start to get plants growing on that sediment, and we start to see the roots decay and add organic matter, the stems decay, we get some leaves and sticks, and we start to see the accumulation of organic matter in that top of that sediment, and that's the formation of the A horizon. So that's actually the first soil horizon to form, and it mixes into that sediment. So now that sediment's becoming a soil. Well, over time, more plants grow, the vegetation gets more lush, you get bugs and animals and insects turning the soil, moving the soil around, and we get accumulation of that organic matter to the point where now that organic rich soil has a higher CO2 content than the surrounding area. And as rainwater percolates through that A horizon, through that topsoil, the rainwater picks up that CO2 and forms weak carbonic acid. And as that acidic water percolates down through the sediments, it begins to weather. It etches the grains of the soil, the mineral grains, the aluminum, iron, and magnesium, manganese, and clay minerals. And it starts to move those minerals down profile. And give enough time, say the surface remains stable long enough where there's no new sediment, that weathering process will continue until it starts to form the B horizon. So here, the B horizon is forming in that sediment. And that B horizon represents the accumulation of aluminum, iron, and clay minerals. That's why the subsoil is often more clay rich. And the aluminum iron is what gives that subsoil that yellow, bright yellow color. So given enough time, there will be another flood, and that new sediment will come over and bury the vegetation in that first topsoil, and we'll get this new sediment over top the A horizon, creating our first buried A horizon. And it also buries our campfire that was there and whatever archaeological sites or remains that might have been there. So that becomes our first buried A horizon. And as the vegetation regrows along the river, the cycle starts to repeat. We get a new accumulation of organic matter at the top on the new sediment. And the important thing is that this new sediment is thick enough that it isolates the weathering from the lower soil horizon. So the A horizon starts to weather at the bottom of the A horizon, the top of the C horizon starts to weather, but the weathering doesn't reach deep enough to affect that buried A horizon. So what happens is we have, as that surface becomes stable over a period of time, we have new B horizon formation. So now we have a second soil, and the AB in partially weathered C over top that buried A and BW horizon and C. BW just means weak B horizon, so it's weakly developed, little b, or the little w. So over time, once again, we get more sediment flooding across the landscape, land surface, across the terrace, and trees grow up bigger. And that new sediment, once again, encapsulates those buried soil horizons. So we get now a second buried A horizon. And once again, the process is just repeating over time. And as time goes by, the terrace gets a little higher, and the flooding kind of often decreases a little bit. and we get a new A horizon as the organic matter mixes into the soil, and insects and roots and all kinds of things help this process along. And we get, once again, we get renewed weathering, and as the vegetation is on a stable surface over time, we get a new B horizon forms. And that's when often we end up looking at these sites and seeing what we can find down deep and doing the archaeology. So once again, here's our profile again. And what we're seeing is those buried A horizons as the soil sediments layers stacked up and the soil forming processes altered those soils into soil horizons. And the key thing here is that the deposition is fairly rapid. It's rapid enough that it removes the buried soil horizon from the weathering process. But not all of our soils in Western Pennsylvania look like this along our rivers. A lot of times we just have thick packages of B horizon and just a single topsoil at the very top. This is an example along the Clarion River in I think it's Forest County. So this is very common in Western Pennsylvania, where we see one A horizon at the very top, our topsoil, and this really thick, deep B horizon. In this case, a BW. It's a weakly developed B horizon. Over top, a BC, a partially weathered C horizon, and a gravel. So how does this form? And how does it differ from the buried A horizon example? Well, once again, we start again with the gravel bar forming along the stream channel. We get our new sediment over top the gravel, and then plants start growing, and insects and all things start happening on the top of that sediment, and we start to increase the content of organic matter mixes into that sediment. The weathering begins as the organics get rich enough to help along that weathering process, and we get our B horizon forming as the aluminum, iron, and the clay starts to accumulate in the top of the C horizon. Then, if it's stable long time, so this is an area where there's not as much flooding, that B horizon will develop even deeper, more deeply weathered over time. So time is the key element. The longer it's stable, the more the weathering process acts on that particular surface. So this is a stable surface over time. But eventually, we get new sediment. It floods again, we get new sediment. But notice here now, the sediment, because maybe this location is a little further away from the riverbank, it's thinner, it's not as thick. And when we get our new formation of A horizon with those organics, it's not as far removed from that other lower A horizon, and it starts to mix together. And when the weathering process starts, the bottom of the lower A horizon starts to leach away and new B horizons forming. So the B horizon actually thickens upward. And then over time, as that becomes a stable surface, we get maybe a new flood sediment, more organic matter onto the surface, mixing in. The weathering process starts to leach away the bottom of the A horizon, that stacked A horizon, and that converts to a B horizon. And once again, our B horizon gets thicker. It thickens upwards. And then the process just repeats. New sediment, organic matter mixes into the sediment, forms a thick A horizon. The weathering process starts, and the bottom of the A starts to leach away, and the soil profile moves up again. Once again, the B horizon thickens upwards. And that's how we get these, what we call cumulative or over-thickened B horizons. And these are very common in our river terraces across Western Pennsylvania, this type of profile. So the difference here between this and the buried A horizons is that we have slower deposition and more stability over the time frame because of where this location might be on the floodplain. Location is important. But what's also interesting to know is that those sequences of B horizon formation actually leave a trace in the soil. It's really hard to see when you're actually digging, but you can actually see the traces of the fine clay with each of those B horizon cycles if you do the laboratory analysis. So here's the difference. With our rapid deposition to the left here, we get our buried, rapid and thick deposition of new sediment. We get these buried A horizons, while maybe further inland on the terrace, the same age, but we have slower deposition. We have a thinner soil package but now we have, instead of those buried A horizons, we have a cumulative or over-thickened B horizon with traces of those soils, those separate separate soil packages. So rapid accumulation versus slow accumulation, and that's kind of what we're seeing here with the difference. Yet the time frame, that 1, 2, and 3, represents those stable periods where there is a strong potential for archaeological remains. They're also present in that over-thickened B horizon, but we just can't see it because we don't see that preserved buried A horizon. And often these buried horizons correlate to different time periods and climatic events. And work by Frank Vento and others in Pennsylvania have shown that these particular periods of time where the climate is more stable results in a more stable landscape and less overbanked sediment, in a stable landform where these buried soil horizons were present, or these soil horizons were present on the surface, stable long enough that people camped and lived on these surfaces. And then they became buried again as the streams became more aggressive during a more unstable time period in the environment. But there are other combinations of soil profiles, and I'm just going to step through these kind of quickly. But they form this, they have the same kind of sequence, but a little different rate of deposition, and usually associated with where they're located on the complex of river terraces. So once again, we're going to start. So we're going to do this, what I call stacked AC horizons, or cumulative A horizons. So we're going to start with the gravel bar again. We get our fresh sediment. A flood comes in, puts sand over top of the gravel. Then we get our A horizon, the mixing of organic matter. But now it's not stable long enough. We don't get the weathering because maybe every 5 to 6 or 10 years we get another flood, and new sediment comes on top of the A horizon. So that's fresh C horizon. That's C horizon of unweathered sediment. And we start to get A horizon formation, accumulation of organics, but then it floods again. And maybe 5, 10 years, we get accumulation of organics again, forming a new A horizon, and then it floods again. And the cycle repeats. More organic matter. It may be this time we're into the historic period, and we start to see the first cultivation with plows and modern agriculture. Sometimes during the historic period where we do have modern agriculture, it floods again, and we see then that new sediment gets plowed into the surface, and we see actual accumulations of A horizons associated with the farming and agriculture. And this sequence of soil often happens on the smaller streams. And often this stacked AC horizons are all related to historic time periods where the cutting of the trees, the forest, and clearing of the landscape is the reason for this more rapid accumulation along the streams. So we have our stacked AC horizons. It's flooding often enough that no B horizon actually forms. It's accumulating too fast for the weathering process to have a significant impact. And then even at the top, we can have these cumulative A horizons where the A horizons stack up, but particularly when it's being cultivated. We have another type of soil. So that last one, the stacked A horizons, is a very young soil. This is a very old soil that forms on stable surfaces. A lot of these landforms, these old river terraces, go back to the late Pleistocene at the end of the last ice age. And the key thing here is that the B horizons, I have them labeled here as BT and BTX. T stands for translocated clay. That means the clay is accumulated over a long period of time. And when we see a BTX, that's where it's almost cemented. The soil almost gets kind of hard. It's really hard to dig if you encounter these soils. And this is an example along the Clarion River. So this is what a typical really old soil profile looks like, that was stable over a long period of time with a minimum amount of flood sediments accumulating. So once again, we start with a gravel bar. We add our C horizon, our new sediment. Organic matter mixes in. We get weathering at the bottom of the A horizon. We start to see the B horizon form, but this is a very stable location. There's not much new sediment. The flooding may be only every 500 or 1,000 years, and that B horizon keeps accumulating, keeps building from the weathering process. It keeps converting that sediment into soil. And eventually, if that continues long enough and it's stable long enough, we'll start to see that accumulation of clay and turning it into a very old BT horizon. Then we do get some floods, some new sediment comes across, maybe that 500 or 1,000 year flood, and we get accumulation of organic matter in the new sediment, and maybe even a BA or AB. It's kind of a transition between the A and the B horizon as it weathers, and eventually, if it's stable long enough, we'll get this accumulation of sediment up through and a new BT horizon. And once again, it's kind of like the cumulative B horizon. It's starting to thicken upwards. And if it weathers long enough, over a long enough period of time, that lower BT horizon will start to harden. It'll start to cement from the iron and aluminum that's percolating down through into clays. And it gets very, very hard to dig. And new sediment comes in and the process repeats, another flood event. But this is over long periods of time. And once again, the weathering process begins again, and the BT horizons over thicken again. Now, and we end up with that soil profile with the very old B horizons. They often tend to be more red than the BW horizons. So what's important here is that these soils can all be found even in one floodplain complex. Now, I mean by a complex is that's a floodplain where there's multiple steps and elevations above the river. So if we start to the left here where the river channel is, our newest floodplain, the active floodplain, what we often label as the T0, meaning terrace number 0. It's where new sediment is being deposited maybe every 3 or 4 years from recurring floods. That's where we see these stacked AC horizons often, or even across the T1 on smaller streams. So the stream or river size has an impact on what we see. Now on the levee deposit, that's on the next terrace up, the T1 terrace. The levee is that right the edge of the terrace where it receives the most energy from the river. So it tends to create a little bit of a hump. And these are easy to see along a lot of our streams and rivers in Pennsylvania. So the soil is a little bit thicker at the levee deposit because it's receiving the direct impact from the river when it's flooding. And that's where we see a thicker accumulation of sediments, and we tend to get these buried A horizons right along that levee deposit. Now, if you walk back further on the T1 terrace, where it's further removed from the stream channel, where the energy is a little bit lower, and the floodwaters are slower, and those floodwaters deposit finer sediments, you might get less accumulation of sediments in those areas, and the buildup isn't quite as thick as on the levee deposit. And that's where we often see our accumulative BW horizons. Even though they're the same age, it's just a thinner sediment package and has been subjected to more weathering over time, and it results in a different soil profile. And then if we go back, in a lot of places we'll see an older terrace that's even higher up from the river. We often relabel this as the T2 terrace. And these are the terraces that often go back to the last ice age, to the end of the Pleistocene. And we find that's where we find these old BT and BTX horizons that are buried. And in these older terraces, most of prehistory we find in the A and the BA horizon, and maybe the early Archaic and the Paleo in that BT horizon. Whereas maybe down on the T1 terrace in that cumulative BW horizon, we'll find prehistory down through that B horizon. And on the levee deposit, that those buried A horizons could have deposits relating to the woodland or Archaic periods as well. Whereas out on that floodplain, where the stacked AC horizons are all there to the left, that might all be historic sediments with very little or maybe just the very latest cultural periods present in the lower A horizons. So there's a sequence of age, and how these soil profiles develop depends on where they are on the terrace complex and the size of the river and the stream and the sediments. There's a lot of different factors, but this is kind of the typical thing we see on a lot of our along a lot of our rivers in western Pennsylvania. So our soil interpretations are very important for the archaeology. It provides information for helping us understand the sequence of deposition and how those different cultural levels get buried and how they change over time, how the soil changes and what that does to our cultural deposits. But it's equally important that archaeology provides information back to understanding the soils for the folks who are doing the soil science in geomorphology, because the archaeology provides ages, dates. You know, we can get the radiocarbon dates on the hearth features. The artifacts give us clues to what the age of the sediments are. And this allows us to track, not only estimate the age of the sediments and when these buried soil horizons were formed, but also it allows us to track these buried soil horizons often across multiple landforms and even across different locations within the river valley. And that really helps guide the archaeology when we go to other locations and other sites that are nearby. So it's very important that we look at the soil to understand the archaeology, but then the soil scientists and geomorphologists need to look at the archaeology to understand the soil. So it's a process that we have to communicate back and forth so we have a better understanding of the archaeological deposits and the natural evolution of our landscapes, particularly in the river valleys. And that pretty much sums up what I have to present. If we want to go on to questions.
Yeah, we actually already have several coming up. So let's see. So just to remind everybody, please use the Q&A box. And if you want to stop sharing your screen.
Okay.
Our first question goes back to the title of your company. They said it reminds them of some Lenape words. Is it Lenape? And what does it mean?
Yes, it's back during the .com era in, was it 99, 2000, everybody was registering their domain name and it looked like they were all going to get used up. So I registered a domain name, Quemahoning.com. Quemahoning is the name of the township where I grew up. So it's Quemahoning Township, Somerset County. And the domain was one of the few that were still available. I registered not knowing what I was going to do with it. And but the main thing is I wanted to have my email address so it would never change.
Nice.
So but then when I decided to form a company doing archaeology, that I figured I had the domain name, I might as well use that as the company name. And it is Lenape. It stands for Pine Tree Lick. That is my understanding of the translation.
Cool. All right. So next one. What is the component definition of clay? What is the typical age and type of clay?
Ooh, clay is a complex issue. So clay has two meanings. One meaning is the size of the particle. So clay-sized particles are smaller than silt. So they're very fine. Silt, if you take silt and put it on your teeth, you can feel the grit on your teeth, but you can't feel silt between your fingers. Sand you can feel between your fingers, but not silt. But you can feel silt on your teeth. Clay you can't feel on your teeth. It's too fine to feel on your teeth. That's one definition, is the size. The other definition of clay is the mineral type. So there's a whole bunch of clay minerals, kaolinite, and boy, I can't even name half of them. But they're probably multiple clay minerals are in our subsoil at any given time. It's not just a single clay mineral, and that takes complex laboratory analysis to determine which clay minerals are actually present.
And does clay typically have an age range that you find clay in?
Well, clay exists in our bedrock, and it weathers out. When the bedrock breaks down, all rocks, given enough time, all rocks turn into sand and sediment. And the quartz grains tend to create our sand particles because quartz is a hard mineral. But there's other mud and other ingredients that were deposited to form that sedimentary rock that was originally clay, and it's some of the cement holding the sand grains together is clay. And when that weathers out, the weathering of the rock will actually introduce the clay into the soil and sediment. And then through weathering, that clay is kind of dissolved. That's probably not the right word, but it's decomposed, and then it recomposes back into clay as it translocates down soil profile. So clay can be as old as can be in the source bedrock and as old as that source bedrock, or it could be newly formed as part of the weathering process. So you can't say that the clay has a specific age.
Okay. Yep, makes sense. Can you, by studying the soils, find evidence of climate and its changes?
Yes. So whenever we were looking at those cumulative B horizons where there was evidence of the fine clay that indicates periods of stability, my work along the Clarion River found that those signals, those indicators of that stable horizons in the alluvial sediments were also present on the hill slopes in the colluvium. Now, colluvium is soil that is washed down from the hill slopes instead of being deposited by the river. But the same signal crossed across those two depositional environments. And what that tells us is that the periods of stability that created those buried soil horizons was affecting both depositional settings. That means it was environmental. So it was a result of the environment and the stability of the landscape, the climate, the vegetation. Animals have a play in this, insects. Whatever was going on, both the floodplain and the hill slopes were more stable and created those marker horizons. And because we found that signal on both depositional settings, both the hill slope and the floodplain, that tells it's an environmental signal. And then we can trace that environmental signal in the sediments and soils across the valley.
This is an interesting one because you mentioned floodplains just now. Can you do soil analysis if you're in a non-floodplain deposition? And is that different?
But the source of the sediment's different. So when you're up on your hilltops, it's the actual breakdown of the underlying bedrock that's forming the new sediment. And the breakdown of the bedrock and the sediment formation and the soil weathering and erosion and deposition, they're all working together, and it actually gets even more complex than on the floodplains. So often, if you dig down through the topsoil, through the A horizon, down into the B horizon, that B horizon on the hilltops can often be very thick, or it could be thin. Depends on the underlying bedrock and how resistant it is to weathering. If it's shale and it weathers deeply into the hilltop, that B horizon might be really thick. If it's on the top of one of our mountain ridges where the underlying bedrock is hard sandstone, that B horizon might be very thin. And so the soil is forming from that rock breaking down over time and weathering. The weathering is the key. It's what releases the different iron and aluminum and clay minerals to form our soil horizons. But yes, the hill slopes and the hill summits, they're even more complicated in some ways.
I'm going to challenge you on a question here. What is the oldest / deepest evidence of a campfire found in the Delaware Valley? Could be
in the Delaware Valley. Well, the Shawnee Minisink site, which is pretty well known. I don't know if they identified hearth features there, but I'm sure those people would have had hearth features. Often the Paleo-Indian artifacts. These are some of the oldest remains in Pennsylvania. And that's what was found there by Joe Gingrich when he did the excavations at Shawnee Minisink. They were down, I think, about 10 feet at that site on the Delaware River floodplain. And if there was evidence of fires there, that would have been some of the oldest in Pennsylvania. The oldest I found was along Red Bank Creek. We dug through a hearth feature at 116 centimeters deep. It was in a BW horizon, one of those cumulative BW horizons, and that hearth feature had two large pitted stones, pitted anvil stones, and a Kirk corner notch point, an early archaic Kirk corner notch point. There was good charcoal remains underneath the pitted stones. I ran a date at two different labs, and the sum of those two dates calibrated was 10,300. So it was a very early date.
Nice. All right, we're going to get some little more technical questions here, and I hope I don't pronounce it wrong. But in the summary slide, is bioturbation evident?
You have to assume bioturbation is always present. I mean, insects, earthworms, trees, they move soil a lot. It's over a long period of time, so we don't always see it, but it's happening. So even if an archaeological site's deposited on an acre, say where that campfire was on the ground surface, as the artifacts are left on that ground surface, things are moving. The soil tends to churn with the insects and plants and stuff. Imagine how much soil is displaced by a big oak tree. I mean, that has an impact. And trees grew on the riverbanks as well, and on the floodplains. So bioturbation has an impact of the soil, and sometimes we can recognize that when we're digging, but a lot of times the soil weathering process erases the evidence of that bioturbation, but we see it in the artifacts, because the artifacts, we might find artifacts in a 15 or 20 centimeter level, separated 15, 20 centimeters, but a lot of times they'll refit. And that tells us that they were deposited at the same time, even though they got separated vertically in the soil profile because of the movement in the soil. Frost and freezing also moves things in the soil. So many things happening. And understanding the soil and studying the soil helps us understand what has happened to the archaeological deposit over time, and gives us information on, how to interpret what we're finding.
Is any buried surface considered a paleosol, or is there any age requirement?
Paleosol has different meanings in different parts of geology and soil science. So in soil science, paleosol is that buried A horizon. In geology, sometimes the buried A horizon or buried soil package that becomes bedrock is called a paleosol. So there's a little bit of confusion there. But for archaeology, when we talk about a paleosol, we're talking about those buried A horizons that I described a little bit ago.
I'm just going to generically say this because there was a question about is there a copy of the presentation? So for anybody asking this, we are recording this session, and anybody who has registered, we will be sending you the link out on that. So that answers that question. What is the practical significance of understanding soil levels?
It helps us understand what we're finding archaeologically. And it helps us to predict where we're going to find archaeological sites. So if we're along a riverbank and I do a soil core or a shovel test, and I see these stacked AC horizons, and they don't show any sign of weathering, I know that the chances of finding an early archaic site is probably next to nil, because those soils haven't weathered. That means they haven't been there long enough. And that the stacked AC horizons may even be historic in age within the last 200 years, which is typically what we find. But if I dig down and I hit that BTX horizon, and it's 50 centimeters deep to that BTX horizon, there's a possibility that you could have a buried, maybe early archaic or Paleo-Indian period site there at a relatively shallow depth. Or if you have those a location where you find those deeply buried A horizons, now archaeologically that's really interesting, because you have maybe a woodland period in the early woodland in the upper buried A horizon and a late archaic in the lower buried A horizon. You have good separation, and that's better for archaeology when you have that stratigraphic separation between your time periods. That makes it so you can study each time period independently, and you're sure that the deeper one's older than the more shallow one. So it gives you a sense of chronology. Whereas on the older surfaces, like the up on the T2 terraces, where everybody from Middle Archaic through Late Woodland, all those artifacts are mixed in the maybe in the plow zone. There's no stratigraphic separation. And it's important to understand in that context that your archaeological potential, you might find lots of artifacts, but maybe you're not going to have good separation between the time periods in that setting. So understanding the soils and what you can expect to learn in those given types of soil profiles helps you make decisions on where you want to dig, particularly if you have specific archaeological questions that you're trying to answer. If you're looking for paleo, you're not going to be down on the T0 surface looking for stacked AC horizons. You're going to be looking for those older soils.
Mm-hmm. Do Pennsylvania canals show us these soil layers?
Well, good question. I've not actually completed any archaeology in a canal basin, but when the canal was dug, the soil layers would have been visible. But often the canal basins I looked at, the sides of the canals are slumped in. So there's been new soil formation along the exposed surfaces within the canal. So you would have to dig into the sides of the canals in order to see the soil horizons, similar to how you would dig into the sides of a riverbank to see the soil horizons. But just the canals, the old canals, without digging into them, I don't think you would be able to distinguish the soil horizons.
It's an interesting one, but is the PaleoDigger machine doing well right now?
I just 2 weeks ago had the PaleoDigger machine along the Potomac River in Maryland. In 6 days, we dug 21 test pits to a depth of 3 meters. And we had artifacts from the Paleo level, from the Paleo-Indian level in most of those test pits. And so we now have over 30 test pits delineating where that Paleo-Indian occupation is on the Barton site is the name of the site. So those 21 test pits that we dug in 6 days, the volume of soil that was removed and screened is equivalent to 5 2x2 meter squares dug 2.5 meters deep. So the machine is proving to be extremely efficient at essentially creating a shovel test pit, but being able to dig down to the deepest levels. So in some test pits, we were down deeper than 3 meters. So we've had great success with the machine at the site.
What are the light colored vertical lines occasionally running down through darker areas?
That's part of the bioturbation, indications of bioturbation, and also cracks that form in the soil as the soil gets wet and dries out. So maybe if you ever paid attention to the ground surface, sometimes when it's really dry in a bare part of the ground, you'll see these cracks. They form these like polygon shapes. Well, that happens also deep in the soil. And where those cracks form, that's a place for water to percolate down through more easily. And you get the lighter killer soil because the water percolating through is removing the iron and aluminum from the soil. That's what makes those vertical lines, those cracks, seem more visible. It also tends to be an indication of age. So we tend to see that in the older BT horizons and BTX horizons. So we pay attention to that. But also roots and animal burrows that fill in. Because the burrow is a little softer sediment, water percolates through those easier, and that water also removes the iron and aluminum as it percolates through and makes those kind of features visible. So it can be the result of wet, dry cycles and also bioturbation from animals and insects.
This is a good overall question, but what factors decide where you will dig?
First, it depends if it's a compliance archaeology project, we're going to have to dig where the project is, where the development is. If it's research oriented, where we can choose where we want to dig, it's the research questions that guide where we dig. What are we trying to learn? Are we interested in a Monongahela village site? Is that what our research question? What we might be asking a question about how Monongahela people changed over time. So in that case, we're going to look for a Monongahela village site, and that's probably going to be in the very upper levels of the soil, even along the larger rivers where the soils might be deep. If we're looking for late woodland village sites, we're going to look in the upper levels of the soil. If we're interested in early archaic and maybe the transition between early archaic through middle archaic, then maybe we're going to be looking for the stacked A-B horizons or the cumulative V horizons, where we see vertical separation in the deposit, so we can see the late archaic or early archaic level, and then we can see the middle archaic level separate, and we can then know which artifacts came from which time period and make direct comparisons. And if we're interested in paleo, then we're looking for those really old soils, and the soils that are old and also down deep enough that they've been well preserved from cultivation and plowing.
Can you use geophysical instruments to understand soils and sediments?
Yes, and we did some of that at the Barton site. Dr. David Leslie came down and he did vibrocores, where they actually took core barrels and the like aluminum pipes and used vibration to sink them down into the ground to pull out cores. And then he ran ground penetrating radar with a low frequency so that it would penetrate deep into the sediments. And he was able to see patterns in the river terraces, so that gave us a little more three-dimensional understanding of the terraces. A lot of these river terraces, especially where the old paleo sites are, during the end of the Pleistocene, the terrace didn't look like it looks today. We have these nice flat, level plowed fields today, cultivated fields. But back when the first inhabitants were entering Pennsylvania, these stream terraces along the bigger rivers probably were undulating gravel bars capped with sand and silt, and probably looked a bit different than what we see today. So the ground penetrating radar and other geophysical methods help us look deep into the river terraces and understand a little bit of the three-dimensional structure of those terraces. We'd be able to see the swales and bars that are buried underneath.
Back to the PaleoDigger, does your company own that, or who owns it?
I designed and built the PaleoDigger, and it's designed specifically for doing archaeology. It's the only machine in the United States like this. It digs the way we dig. It digs the same way as archaeologists dig test pits, except it does it with a machine instead of a shovel. The test pit is 52 centimeters in diameter, which is about 20 inches. We can remove soil 10 centimeters at a time, and at this point, I can go 7 meters deep, which is about 20 feet. And it's once you get below 5 feet, it becomes difficult to dig deep because of OSHA requirements, safety requirements. You really don't want to have workers down in a deep hole because of the threat of the wall collapsing in. It's very dangerous. So the machine allows us to test soils down very deep without having workers go in those test pits. And it does it very efficiently. And we're finding that it works extremely well. I've used it for 3 different PennDOT projects now along the Susquehanna River, and for a project for American Electric Power along the Roanoke River in Virginia. And all 4 of those 4 projects were compliance related archaeology.
Do things like earthquakes ever change the soil levels?
Yes, but we don't see it in Pennsylvania. Some years ago, I was visiting western Wyoming, and we were traveling on the highway outside of Jackson Hole, and all of a sudden, I was a passenger, and I said, "Oh, there's a dig site." So we turned around, went back, and it turned out that it was the Wyoming State Historic Preservation Office, their archaeology crew was working. And we introduced ourselves and said we were from Pennsylvania. And the crew leader said, "Hey," I said, I said I do soils and stuff. He said, "I want to show you something." So we walked down away from the rest of the dig, and he opened up a test pit, and there was a glade soil horizon. So glade soil horizons form in wet soils. And what happens is, because they're wet all the time, like in a swampy area, the iron and aluminum are completely washed out, leaving just behind the quartz minerals, which makes it gray colored. But the soil horizon he showed me, this gray glade soil horizon, was tilted at an angle. And I said, "How in the world do you get a glade horizon tilted at an angle?" And he kind of grinned and he said, "Teton," he pointed to the mountains, the Teton Mountains. He says, "We're still tectonically active here in Wyoming." So it was formed horizontally, but then over the last 10,000 years, the whole region was uplifted tectonically, tilting those soil horizons. So that was a lesson for me on tectonics and soil horizons. And tectonics in general is slow movement. Earthquakes are part of tectonics. So yes, earthquakes and movements of the crust and mountains rising can affect how soil horizons form over time.
Well, thank you to the audience for your questions. Brian, we have one final question. What would you like the audience to remember from today's presentation?
Soil forms in sediment. A lot of times people say, well, the A horizon was deposited or the B horizon was deposited. No, the sediment comes first. That's the deposit. Then the soil horizons form in that sediment. Soil horizons form over time within existing sediments, and that the more deeply the soil horizons form, the more deeply the B horizons form, the more weathered they are, the more the older they are, in the sense that they've been stable over time. So that buried A horizon doesn't represent a depositional time. It represents a period of time that surface was stable. So it's not deposition, it's stability over time. And that's the important thing, particularly for archaeologists to understand.
Well, thank you for today's presentation.